Welcome once more to LGAD's Triple E tutorials. Today we'll be looking at question number 5A of the Field Theory 2 2020-2021 section, Rivers State University Electrical Electronics Department. The question says derive the expression for the characteristic impedance of a two-conductor transmission line with center-to-center conductor spacing of 2A diameter and a conductor diameter also of 2B. Please, before going to this question, please don't forget to like and subscribe. Thank you. Welcome guys to another section of LGAD Triple E tutorials. Now looking at the question 5A, when they tell you about center to center, what they are trying to tell you is that you're having a co-axial cable. Now if you look below, you're seeing a diagram of a co-axial cable. It has a conductor inside and a conductor outside. So each of them are connected center to center. Now this is the center of the conductor inside. Now if you see from here to here, depicts the diameter of the inner conductor. If the radius of this conductor is B, the diameter is 2 times B. That's what you're seeing here. Same thing goes to the outer conductor. The diameter is 2A. It means the radius is A. So the diameter is what? 2A. Now, one peculiar characteristics of conductors that are placed side by side is that the electric field flows from one edge of this conductor to the other. So if you see these lines here, they indicate electric field. And the space between is the electric permittivity of the media. That's what you have seen here. Now, this inner conductor has a positive charge and a negative current. And there's a negative charge and there is a negative current. Now if you're looking inside this inner conductor, you can see these lines in the space between the inner conductor and the outer conductor. You see these circular lines which form annular rings. They are as a result of the magnetic field flowing through these conductors. So with this now, we can actually, with this diagram, we can actually get the capacitance and the inductance of this coaxial cable and relate it to get the impedance of this transmission line. And the capacitance exists between these two layers. You see this space, these guys here, this space here and here, it's the capacitance exists between here. Now if we look at Gauss law, from Gauss law, we know that the electric field intensity is equal to E is equal to the line charge density divided by 2 pi electric permittivity times the radius. Now this line charge density is the same thing as saying charge per unit length. Now if you observe from here, I said there's a charge here. Now this charge is considered per unit length. It's not just considered as a charge. Is considered as per unit length charge. Then also we recall that V, which is your potential difference across the two cylinders, is equal to E times D. E here represents electric field intensity, where D represents distance. In our case, we are taking it to be radius. Now if we consider a particular section from this two-cylinder scenario, we can actually analyze the voltage across the surface of the centers of the two cylinders. So that's where we bring in V to be equal to the integral of the upper limit to the lower limit of E times the arrow. That's E times delta arrow. That's the little section we are considering.